Alrighty, so here we go with chapter 12, section 2 for geometry, about arcs and chords. Today, our objectives are to apply properties of arcs and apply properties of chords. And remember, in our magic circle activity, we did talk about an arc, that distance along a circle, and then a chord, which was across a circle. So we'll go over those definitions here. So first thing we're going to start with, and you do have some fill in the blank ones here. A central angle is an angle whose vertex, which is the center of the circle, so this guy here, is in the center of a circle. So it doesn't necessarily show it in here, but right here is our vertex. And a central angle would be this one right here, central angle AB. All right, so then we have our arc, the unbroken part of the circle consisting of 2 points. Called the endpoints, and the points on the circle between them. Alrighty. So our intercepted arc is this guy right here. So that's the arc, it's the outer part of the circumference, but the central angle is this measurement inside here. All right, so that's your central angle, piece of the pie there, and then the arc, which is the crust of the pie. Alrighty, so when we talk about arcs and their measure, we have something called a minor arc, and we then have a major arc, and then a semicircle. So we'll kind of talk about what each of those are. But a minor arc, if you could believe it, has points that are on the interior of a central angle. So whose points are on or in the interior, of a central angle. So here's our minor arc, AC. What happens is a minor arc is less than half of the circle. So I'll write that over here. It kind of reminds me of an acute angle and how that is less than 90. Technically, a minor arc here is going to be less than 180 because that's half of the circle. So this one here, again, less than half the circle, minor arc. We get to name a minor arc with just 2 letters. So because it happens to be less than 180, that central angle, again, because it's in the center of the circle, because there will be ones where they are on the circle and create an angle. So central angle from the center. And again, this measurement needs to be less than 180 to be a minor arc. Then over here we have our major arc. And your major arc, officially in the definition, is an arc whose points are on or in the exterior of a central angle. Exterior of a central angle. And what that just means is that if we look at this diagram here, we're actually talking about this arc measure. So all the way around. So of course, in order to not say that that's arc AC, because it technically goes from A around to C, that's also what this one does. It goes from A to C. So to be able to say that it's this larger side over here, this major arc, we're going to end up actually using 3 letters. So those 3 letters is because it's going back around, and it's going to be larger than 180. So this one, again, a major arc, is kind of thinking of like that obtuse angle idea. All right, and then in contrast with less than half of the circle, this one is more than half of the circle. So usually more than 180 degrees. All right, then the last piece, knowing that we have two small and big, this one is actually the middle. So in that case, it is exactly 180, half of the circle. And so it's the endpoints and how those lie on a diameter. Because remember from our previous lesson in 12.1, diameter is half of the circle going through the center. So it does need to include the center point. And so EFG is going to be our semicircle. And notice that it also has 3 letters. I suppose you could get away with 2, but again, then you might think that it's less than 180. So we are going to, again, use 3 letters. Alrighty, so those are kind of our main ideas, how to label a minor arc and what it means. It's less than half. Major arc, how to label it and that it's more than half of the circle. And then a semicircle, which is semi of the circle or half of it. So, all right. Again, just to reiterate, when we are talking about writing minor arcs, they need to be named by 2 points. And major arcs and semicircles must be named by 3 letters or 3 points. And of course, double checking that those 3 points or 2 points are capital letters, because that is how you indicate a point versus a side length. All right, so here's a first example about data. A lot of times when we think of central angles, we use pie charts. So here we are with our first one here. The circle graph shows the types of grass planted in the yards of the neighborhood, and we need to find KLF. And notice that it has 3 letters in it, so we are going to find that major arc. So if we follow from K to L to F, that's here where they're talking about centipede grass. So we want to find this arc measure. The interesting thing about an arc measure is that it is not the same as an arc length, because that would be the distance. The arc measure is actually just the angle. So we want the angle in degrees here. Notice that it says that it's 65% of this circle. And of course, there would technically be 100% in this circle, which is weird because when you think of circles, hopefully you think of a total of 360 degrees. So there's a few ways that we can go about doing this, but the easiest one is to understand that concept that I just said. Normally, 100 is your percent total, but in a circle, we're talking about 360 degrees total. So if we set up a proportion, knowing that centipede grass is 65%, we could put that over 100 and then find out how many degrees that central angle is. So if we cross multiply 65 times 360, 65 times 360 is 23,400. And then technically that still equals the other diagonal, which is 100x. And so then to solve, we would divide both sides by 100, meaning technically get rid of these 2 zeros. And so in that case, 234 is our x degree measure. Or more particularly, our measure of KLF, this little arc above it. So again, the way that we figured out what this again, larger than 180-degree measure was that we noticed that 65% of 100 was the centipede grass. And so we just want to know how many degrees out of the whole circle that was. Alrighty. The next piece talks about adjacent arcs. And adjacent arcs are just like we were talking about with trig. Adjacent means next to, so they are arcs of the same circle that intersect or share exactly one point. Okay. So in that case, RS and ST, again, this is their shared point. Are adjacent arcs. So here we are, RS, this one, and ST, this one. Whatever those central angles happen to be, those would be adjacent arcs. The reason that we want to know what adjacent arcs are is because, oh my gosh, we can add arcs. Okay, so this postulate here, again, postulate just means a rule. So in this arc addition postulate, guess what? You can add arcs together to get the entire arc itself. This one here is mentioning that it's larger than 180 degree or a major arc, but of course this picture doesn't necessarily show that it's larger. But remember that we don't necessarily use diagrams for their measurement, but we do use them for just kind of placement. So either way, the measure of an arc can be formed by adding two adjacent arcs. Yay! All right. So then we're going to use that idea of arc addition, and we are going to find BD. So it's always nice to know exactly where you are trying to find the measurement of. So again, this entire arc here. And remember that we're not trying to find the length of the arc, we're trying to find the degree. So we don't know what that degree measure is. So taking a look at what we have, remember that we do understand things about, for instance, vertical angles, right? Okay, so if we remember back to just angles in general, if I have two straight lines, which this one is considered to be straight, and this one here is straight, that means that this angle that's 97.4 is the same measure as this one, because they are vertical angles. It also means that whatever the sum of this is going to be would also add with that. Another thing that we know about angles, and in this case a line, these should add to be 180. So 97 plus whatever this measure is should equal 180. So if we take 97.4 away from 180, we're going to get 82.6 for this measurement here. So 82.6 degrees is this pocket here, which, as I mentioned before, is going to match this pocket here. So if there's supposed to be 82.6 in this pie piece, and there's 52 being taken out here, we can go ahead and subtract 52 from that 82.6 and get 30.6. So now, based on the idea of vertical angles, another set of vertical angles, linear pairs, we now have the measurements of all of the angles inside of here, which means that if we want to find BC, we can just take the measure of BC, add it to the measure of CD, and we'll get what we're trying to find, which is the measure of BD. So the measure of BC is 97.4. And the measure of CD is 30.6. And so together, that's going to be the measure of BD, which is what we're trying to get. And so the measure of BD is that sum. So very nice, 128 degrees. Again, it's degrees because we are talking about this central angle and not the length of it. These should be arcs here. I kind of made a sloppy one, so just try to make a curve versus a line. because we're not talking about segments anymore. Alrighty. Next one can use the same idea. So again, going back to, for instance, any line going through the center here is going to be a straight line. So KN is a straight line and MJ is a straight line. We also know then that, for instance, this angle measure, which is 25, is going to match this angle measure because these two form an X. And so 25 degrees is going to be in this pi piece as well as that one. Before we get too far, we also are trying to find JKL. That's what our measurement is. So this is what we're trying to find. And I did end up finding part of that right now. Another thing that we know is that if we have a line like this one, there should be 180 degrees. And so if we already have 40 used and 25, that means that the leftover is 115. Because again, 180 for this entire line minus 40 minus 25 makes 115. So officially, in order to find the measure of JKL, we're going to take the measure of JK and add it to the measure of KL. So those two together are going to be 25 plus 115. And so the entire measure of JKL is going to be 140 degrees. So again, we used vertical angles, the 25s. We used the fact that a line makes 180 degrees. So all of this up here should have added to 180. And then we added our two central angles to make the one angle or arc. All right. Then if we move on here, we're going to get some of our theorems. So if you watched the 12.1 lesson already, I kind of have some fancy nicknames for these. But the idea here is that we have arcs and chords that are the same measurement. And so because the chord or the arc or the angle are equal, the other three pieces are equal. So if you have two arcs or two chords or two central angles, you have everything else the same as well. So for instance, congruent chord would lead to the fact that you have congruent arcs, which would lead to the fact that you have congruent central angles. I'm trying to underline here. So if you have one, then you have all the rest of them. I do call this one the Ladybug Theorem. You can actually see it in one of the examples, which is actually the next one, a little bit easier. So converting this into kind of a ladybug, if you will. We've got our little guy with a little head, and then we got some polka dots, yeah? Okay, so anyway, I call this one the Ladybug Chair. It's a little harder to draw on this one, but the idea is still there, kind of drawing our little head and however you want to make it look like a ladybug. The idea behind it is that perhaps you would understand that a ladybug is going to have two of the same wings. So hopefully, unless it's got one and then it's kind of flying around in a circle. So the idea is that their chords or their wings, all those pieces are congruent. So the chords, the arcs, the angles, they're all going to be the same. Otherwise, the ladybug is going to crash. So that's that. So going to our next example, which I've already indicated is going to be the Ladybug Theorem, we are going to find some measurements. And these are going to be quite simple. In fact, the one on the test that I'm thinking of is pretty much, oh, that's that. Okay, well, then that must be it as well. This one here is a little bit more algebra intense. And so you need to take the fact that this chord measurement matches this chord measurement. And so therefore this arc measurement needs to match or equal this arc measurement, which they're giving in this expression. So again, TV and WS sets us off to understand if they are congruent, then we have the Ladybug Theorem. Okay. Then if we need to find WS, so once we find out what N is, we'd plug it in and find this measurement of WS, notice arc WS. So officially we're going to take 9N minus 11 and set it equal to 7N plus 11. Because if these two chords are congruent, then we are going to have these two arcs congruent. So the measure of WS, the arc, is going to measure the match the measure of TV. All right, so algebraically, that just means that we're going to move our pieces over to be with each other. So 9N and 7N makes 2N. Add another 11 to both sides, and we get 22. Divide both sides by 2, and you get an N of 11. Again, that's not the answer. They want you to take that N, put it back into WS, and so we actually get 7 times 11 plus 11. So 77 plus 11, so 88 degrees for that arc measure. So again, the measure of WS is 88 degrees. Arc WS. Alrighty, so there's your Ladybug Theorem. The Ladybug Theorem also works knowing that we have two congruent circles. So if we have two congruent circles, like the notes from 12.1 indicated, circle C and circle J are the same. That means that their radii are the same. And so technically this image could be in this same circle. They would fit. Then they're giving us now that the central angles are equal. And so again, this statement is identifying that we have central angles that are congruent, and so therefore we're using the Ladybug Theorem. And so again, to make the ladybug not flop around too much, everything's got to be the same. So this angle indicates that this chord and this chord are the same measure. So officially that means that DG is equal, the measure of that segment is equal to the measure of the other segment, NM. So if they want us to find NM, we will get what T is, plug it back in, and get our segment. So DG is 14 T's minus 26, and NM is 5 T's plus 1. And then we would go through solving, so subtract a 5T to both sides, and get 9 of them left. Add a 26 to both sides, which makes a nice number that's divisible by 9. And so officially our T is 3. Plugging that back into NM, which is what we're trying to find, we're going to get 5 times 3 plus 1 instead of T. So 15 plus 1, so 16. And so again, 16 is the measure of NM. Oops. That's an NN. Is the measure of that segment. Alrighty, so there it is. Again, how did we know we were using the Ladybug Theorem? They told us that the circles were congruent, meaning that if the circles were congruent, the central angles had to be congruent, and therefore making these same triangles. They're actually isosceles triangles, and so they have the same base. By, it turns out, side angle side, if you wanted to go back to that. All right. The last theorem here has kind of a dumb name, but hey, I call it the computer mouse theorem. Okay, so if you bear with me here and think back to like a Mac PC, like old school, the ones that were like colored and stuff. Anyway, you could Google it. They had these little round mouse or mice. And so you'd have your left click and your right click, and then your cord kind of came off here. Okay. So anyway, everyone's got trackpads now, so it doesn't really matter, but that's what I think of. So if you have a better name, super. So the idea is in the computer mouse theorem that in a circle, if a radius or a diameter, because a radius is technically part of a diameter, so we could just extend that line if we want. Either way, if that radius is perpendicular to a chord, which in this case is EF, then it bisects the chord and the arc. So officially, this setup leads to this idea that this is bisected, so congruent, and then also they said the arc here as well, so the arc. This one here is now going backwards and saying, oh, if you happen to know that that is cutting it in half, then you can lead to the two arcs being the same. So again, one of them is kind of the forwards and backwards, but either way, they both mean that if you have a radius or diameter that cuts a chord at 90 degrees, you must have cut it in half. You also cut that arc in half as well. And so if you have that half, then you can go back to having the radius being perpendicular, whatever you need. A lot of times with this one, we end up actually drawing this triangle because this triangle has now constructed two radii as well. And so we now have an isosceles triangle and two right triangles. Either way, this kind of comes up a little bit as well. So something to look forward to. All right. So this is the next one. And we are trying to find NP. This is actually the last one. So NP is the length of this chord. And if we think back to what we just had, if this is the radius, which we know it is, and that radius met this chord at 90 degrees, we have officially cut this chord into two pieces that match. I don't know what those two pieces are, but I do have an indication of how to get them by the fact that this radius is RM, radius, and it's 17. How do we know that the radius is 17? Because it's saying that this piece here, R to S and S to M, are 8 and 9, so 17. So. All right. So that means that this length, notice that they drew this radius for us, is also 17. And so we can actually find this side by realizing that this 90-degree angle is also over here. And I've made a tiny little right triangle right in here. So I now have a hypotenuse of 17, a base of 8 here, and I just need to find the height. So a side problem is going to be this red triangle that has a base of 8 and a hypotenuse of 17, and we don't know what that side length is. How do we find that side length? I suppose we could do some trig if we really felt like it, but let's go with Pythagorean theorem. So Pythagorean theorem tells us that if this is the C side and this is the A or the B side, that in order to get the missing side, we will fill in A squared plus B squared equals C squared. What kind of interests me a little bit about our class is that for some reason, this seems mysterious. So it shows up a lot more than you would think, okay? And always with right triangles. So anytime that you are missing a side, don't just jump to trig. Maybe you can go a step backward and just use Pythagorean theorem. So always using side lengths with Pythagorean theorem. All right. Another thing that kind of scares me about this and our class is that a lot of times we can't solve this. So I'm going to show all of the steps just to double check that we know what's happening. A lot of you will just put in the numbers here and always leave this one blank, but that is not how it goes because C is the hypotenuse. So I've got my A squared it, my B squared it, and now I will find the C. So without going or skipping too many steps, 64 is 8 squared, and 17 squared is 289. So now that we have this piece, we are trying to find what x is. So let's move this positive 64 over to the other side. And again, some of you would do this too fast and you would say, oh, okay, well that means that our x is 225. But you didn't actually bring down the x squared, which is what it is. So now to solve, we're going to take the square root of both sides. And so our x value, or that height of that triangle, is going to be the square root of 225, which is 15. So now we know that this side length over here is 15. We can write it in here as well, 15. And so again, if I'm trying to find NP, and I know that NS, or this top piece, is 15, then this bottom piece has to be 15 as well by that computer mouse theorem. So the entire length of NP is going to be 15 plus 15. All right. And again, this came from the fact that NP is actually NS plus SP. And NS we found to be 15. And so SP must be 15. And so that is 30. So the measure of NP is 30. Alrighty. So hopefully, again, Pythagorean theorem is going to show up a lot, especially anytime that you're going to talk about things being perpendicular or 90 degrees. Okay, so always look for that and realize that maybe there's some sort of right triangle hiding in there. All right, so that is our 12-2 notes. And what's expected of you is now to work through the 12-2 assignment. Do the 12-2 assignment on your own on another piece of paper, or print out the actual assignment, and then check your answers with the answer key. And if that doesn't help and you can't work backwards, then you can watch the next video where I go through the entire 12-2 assignment just in case you have a question. All right. Don't forget to upload your assignment to HeadRush. Turns out that only like 4 people did that yesterday. So let's actually do that. Okay. Upload to HeadRush. Thank you.